Fundamental Theorem of Calculus Part 2 is often called the evaluation theorem because it gives us a shortcut for evaluating a definite integral. So of course we're talking about continuous functions like f over an interval from a to b, and we're using capital F to refer to any antiderivative of little f. What we're saying here is that if we can find an antiderivative for this integral, so if we can find a capital F function, then we can evaluate the definite integral simply by evaluating the antiderivative at the endpoints of the interval and then finding the difference between the two. This completely bypasses the need for Riemann sums and makes our life much easier. So we're very happy with this theorem. In fact, we're going to use it almost every time you integrate. You'll use the Fundamental Theorem of Calculus Part 2. So let's start off by looking at example 520. This example shows us how to evaluate an integral using FTC Part 2. So the integral we're starting with has a lower limit of -2, an upper limit of +2. The function we are integrating is t squared minus 4. So first, let's remember how to integrate using our shortcut rules. So we briefly talked about this at the end of chapter 4, but then we switched gears and started talking about Riemann sums. So let's remind ourselves that for any power, let's say we have a function like x to the nth power, if we want to integrate that, we are reversing the power rule that we learned from derivatives. So we add 1 to our exponent, divide by that new exponent, and then we add a c, a constant, so long as there are no bounds on our integral. And then we're also taking the integral of the constant. So let's also remind ourselves how to integrate a constant. Let's call a general constant k, and if we want to integrate that constant k with respect to x, we think about the types of functions whose derivatives are equal to constants. Those are functions where you just have constant times x to the first power, for example. And then, of course, any constant c could be added to that to create another antiderivative function. All right, so we have our two integration rules that we'll use, one for each term. Let's go ahead and apply them. Integrating t squared, that becomes t cubed over 3. Integrating -4, that becomes -4t. And we're going to evaluate each of those terms between -2 and 2. This is a new notation using a vertical bar and copying our bounds over. See, we dropped the integration symbol because we did apply the operation of integration. So we're not going to continue to write that integral symbol, but we need to copy those bounds over. And so this is what we're doing. We're replacing the integration symbol and the bounds with this vertical bar and the bounds written there to say, don't forget to evaluate between your bounds. This is where FTC Part 2 comes into play. We found, oops, I forgot my plus c, we found the antiderivatives for the function that we integrated. Now we're going to evaluate them between our bounds. We have the upper bound b goes into the antiderivative first, the lower bound a goes into the antiderivative second, and then we find the difference between the two. So we're going to plug 2 into our function. That's going to become 2 cubed over 3 minus 4 times 2 plus c. Then we're going to subtract the antiderivative evaluated at -2. So we've got -2 cubed over 3 minus 4 times -2 plus c. And then we're going to simplify this the best we can. Our final answer comes out to be negative 32 over 3. And along the way, you might have noticed that the plus c at the end of our antiderivatives actually disappeared. They canceled each other out. And so this is a nice consequence of the FTC Part 2, that when you're calculating a definite integral, one that has bounds on bottom and top, the plus c is really insignificant because you're going to add and subtract that same constant, which we did. We carried it all the way through our calculations. And at the very last step, we noticed that we had a positive c and a minus c, and this will always happen. So when evaluating a definite integral, it's not necessary to write the plus c. Polynomials are fun to integrate because that shortcut rule for integrating is easy. Add 1 to the exponent, divide by the new exponent, move on. However, some functions aren't polynomials, and they often take a little bit of algebra before you can integrate them easily. For example, 5.21, we're integrating this rational function that has a radical in the denominator. We don't have a shortcut rule for this. So we're going to do the best we can to work on that function inside of the integral so that it is something that we do have a rule we can apply to. So I'm going to take x minus 1 over the square root of x, and the first thing I'm going to do is separate it into two terms, so two separate terms. Anytime you have a fraction with addition or subtraction in the numerator, you can do this. So we can have x over root x minus 1 over root x. Double check that you agree with that you can convince yourself that what I have on the right side of my equal sign is exactly equivalent to what I have on the left of the equal sign. Once we've separated our terms, we can then simplify using our exponent rules. So x divided by root x, well, let's rewrite those with rational exponents. So our numerator is x to the first power, our denominator is x to the 1/2 power. And if we simplify our x over root x, we can just subtract our exponents. And then the second term, x to the, 1 over x to the 1/2 can be rewritten using a negative exponent. And so we end up with x to the positive 1/2 minus x to the negative 1/2. And because we just used legal algebra steps to get here, we know that it's exactly equivalent to the rational expression we started with. So we're going to go ahead and replace what we have in the integral with the new version of the function. And this is just another power rule. So we have x to the 1/2, that would become x to the 1/2 plus 1 divided by 1/2 plus 1. And then minus x to the negative 1/2 becomes negative 1/2 plus 1 divided by negative 1/2 plus 1. I don't need a plus c because remember that will be eaten up when we evaluate our integral antiderivatives between 1 and 9. Let's go ahead and clean this up though before we plug in 9 and 1. X to the 1/2 plus 1, that's the same thing as saying x to the 3/2, which means we're dividing by 3/2. The next term, x to the negative 1/2 plus 1, would become x to the positive 1/2 divided by positive 1/2, evaluating between 1 and 9. Dividing by fractions is overly complicated, so I'm going to flip my fractions and multiply them. So I've got 2/3 x to the 3/2 minus 2 times x to the 1/2, and we're evaluating from 1 to 9. Now we're ready to evaluate. So first I'll plug in the 9. Then I will subtract my antiderivative with 1 plugged in. clean this up the best we can. And our final answer here is 13 1/3, or if you wanted to write this as an improper fraction, 13 times 3 is 39 plus 1, so we've got 40/3 for our final answer.